No, veramente? Ah, Peppino, che ci fai qua? No, no, non posso ora. No, 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 devo fare lezione. Yeah. So, all right, guys, excuse me. All right, welcome back. We are gonna focus now on messing with Android apps. What I mean with this, I mean taking these apps and somehow understanding, what's going on inside them, and unpack them and inspect their details, and and again, uh, let's see if they hide any secret. All right, so first of all, we're going to try to understand in more detail how we go from source code, so Java or C++, to an APK. And the actual goals are to learn as much as possible on what's going on under the hood. And the actual goal is to understand how to go from an APK to a higher level representation. Why do we want to do this? Well, because, sure, we are learning how to write apps from source code and transform it in APK, but in the real world, what we usually need to do is the opposite. We start from APKs, so from compiled application, and we need to somehow understand what they're actually doing, okay? And again, the best way to understand how to go back is to understand how to go forward. All right, one slide on the compilation process. So up to now, we focus on this part. We write code in Java or in Kotlin, and somehow there is the Java compiler called JavaC that transforms Java bytecode to .class or .jar Java bytecode. Okay, and again, we're going to see a bit about what this means. Alternatively, you can write in Kotlin, and there is a Kotlin compiler called Kotlin C. And again, the idea is that it transforms Kotlin to Java bytecode. So again, no matter what you do, Java or Kotlin, we go to unified representation called Java bytecode. Then, from this Java bytecode, what the Android Studio toolchain does is to go from the .class to the .dex, from Java bytecode to W bytecode. And the tool that actually does this under the hood is called DX, the DEX compiler. Okay? The idea is the following: that Java bytecode is actually, in theory, executed by the Java virtual machine. What does it mean? Well, it means that it's some kind of intermediate representation, and this intermediate representation is not machine code that can actually be executed by a processor like Intel processor or ARM processor, but it needs to be executed by, again, a virtual machine. Java bytecode executed by the Java virtual machine. So Java virtual machine can be seen as an executable, a piece of code already in machine code that is actually executed by your processor, that takes as input the Java bytecode and somehow execute each instruction of the bytecode, and somehow perform the execution of the bytecode indirectly. Okay, so for example, the Java bytecode could have instructions to move a content from one register to another one, or things like this, or to invoke a method. Well, this cannot be executed by a real processor, but they can be executed by the Java virtual machine. What's happening in Android is that we don't have the Java bytecode, but we have W bytecode, and this is executed by the W virtual machine. Again, it's a kind of very high-level description. As we'll see, as of now, there is no real W virtual machine. It's a bit more complicated. But again, the idea is that the applications, you go from Java or Kotlin, we go to W bytecode, and that's what's contained in the actual application you compile. And then somehow the Android framework or the Android phone managed to execute this W bytecode. Again, we're going to see all the details today. On the other side of things, we can also write pieces of applications in C or C++. Okay, and this is normal C++ code. So once we compile it, you compile it directly to machine code. In Android apps, usually this machine code is compiled to .so files, shared objects. And so I have some slides later on the class about this topic, but the idea is that from C++, you basically build libraries, and usually the name is something like lib peppa.so. Okay, and if you check this .so contains machine code. Okay, awesome. So Now, once we compile it, we have an APK, as we've seen last time. Okay, so an APK is kind of a zip file. Okay, and you can actually run this command. You can do unzip and of the actual app.apk. And if you do this, you're going to see something as output, and it's going to be the Android manifest compressed. So you're going to take the Android manifest, but if you try to read it, you're not going to be able to read it because it's compressed. Then the classes.dex, this is the raw Dalvik bytecode. Again, if you try to open it, you don't understand much. And today we're going to see tools to somehow try to parse the content of these files and somehow try to get a meaning out of them. Okay. Then we have resources.arsc. Again, these are the resources and they're again compressed. And then we have a bunch of XML files under the rest folder. Again, all of this is compressed. So if you do unzip of an APK, you can see something, but you cannot see much because either it's classes.dex or it's compressed XML files. Okay, so let's try to understand how can we actually read these files. Before we do this, more notes about this bytecode. I already mentioned something in the first slide. So once you have the bytecode, this bytecode cannot be run by your processor. Okay, it's code that can be run by a virtual machine. So Java virtual machine runs Java bytecode, Dalvik virtual machine can run Dalvik bytecode. So the Dalvik virtual machine or DVM, what is it? It's actually a program, okay? So it's a program which your machine can run. So once you have it on your phone, it's actually a program in machine code. And it's a program that was written by Android team, Android developers. And this was written at the beginning in C and C++, okay? And so they have the DVM code, actually C++ code compiled to machine code. And now this is a program. This program takes as input Dalvik bytecode, this class.dex, and somehow executes it, and the intended behavior pops out, in a sense that the intended behavior is implemented in Dalvik bytecode, and this is executed by the DVM. All right. All right. So what does the how does the Dalvik bytecode actually look like? It looks like this. Again, this is not classes.dex. If you take classes.dex, it's so compressed, it's a bit complicated, but there are tools that which we explore today that somehow can transform this class.dex file in the APK to some kind of human readable representation. And it looks like this. This human readable representation looks like this. You have the definition of a method. Again, this maps to a method in Java. You have the name, you have the arguments, you have the return value, and then you have how many registers you have or what you're doing. Okay, you're invoking a method, and you're taking the result, you're putting it here. Here you're adding two integers, and so forth. Okay. So today we're gonna try to zoom in on this to understand what really is actually going on. This is just to give you a very high level idea. Again, if you don't understand many things from this one, it's okay. I just want to convey that from this Dalvik bytecode, we can get to some kind of human readable representation. And today we learn how to read this human readable representation. So again, before we dig in the details, one question that could come up is why a virtual machine? Well, the idea is that the same Dalvik bytecode, again, this classes.dex, can run on multiple devices and architectures, okay? And is only the DVM that is custom for each architecture, okay? So you can have different kind of architecture. It could be ARM processor, Intel processor, and so forth. The Dalvik bytecode per se never changes, okay? So you have a DVM for Intel, DVM for ARM, and then the same Dalvik bytecode can be fed in the DVM for Intel or can be fed in DVM for ARM, and everything is going to work. Okay, so if you have an Android app, you compile it to Dalvik bytecode, you don't care what kind of processor you're going to execute this Dalvik bytecode on, because what's going to be executing it is the DVM, and then there is going to be one custom DVM, but then the bytecode is always the same for ARM, for Intel, and so forth. Okay. One other advantage that you see online is, we have a virtual machine because there is a security benefit. Since all the different apps are run in a virtual machine, the app code is isolated, so it cannot actually tamper with everything else and so forth. All right, this is absolutely false. You see many claims of this kind online. Please do not fall for this. I'm going to ask in the exam for sure about this, so please do not get fooled. One possible confusion is that virtual machine can be intended as a virtual machine in terms of some piece of code that executes bytecode, but you probably are aware of other virtual machine like Android emulator, like VirtualBox, like VMware, and so forth. These are two different kind of virtual machines. The ones that execute bytecode, if the bytecode says open this file or delete this file, the actual file could be really deleted depending on how it's implemented. Okay, while on a virtual machine like in VirtualBox, that's really a different story. In VirtualBox, you really install a different operating system. Applications are running on top of this emulated operating system. So whatever you do inside doesn't really affect what's happening outside. So usually there is some kind of security barrier in these virtual machines like VirtualBox or QEMU and things like this, but that's not the case with the virtual machine that implement or that execute David bytecode. Okay. Again, about this security benefit, the counterexample that there may not be any security benefit is many applications are actually written in Java, and Java is compiled to Java bytecode. And so many applications, once you run apps written in Java, what's actually happening is that you use Java virtual machine to execute Java, but of course this is a process on your machine, and if this process is malicious, it's going to do damage. So again, depending on the context, there is no security isolation, there is no security benefit. In Android, as we've seen last time, there are many security barriers, but they come from different places. For example, if you install two different apps, usually these apps have a different user, and this is a different Linux user. And the way it's set up is that these apps cannot really interfere with each other. But this is independent from the fact that this is a virtual machine or not. As we'll see, this kind of security barriers of two different Linux users are also useful when sandboxing or when separating native code for which there is no virtual machine. Again, these are different arguments to convey the virtual machine per se does not get you much security. And if you see something like we use virtual machines in Android because of security benefits, please call bullshit on them. Okay? Cool. All right. Another property of this David bytecode is that once you get this David bytecode, before it's actually executed, there is another component that is called David bytecode verifier. And the way it works is that really you try to execute this David bytecode, the verifier kicks in before executing it and checks some properties and checks that it is well formed. And it turns out that this verifier checks that you don't do weird tricks. And this implies that you really cannot do weird tricks. Okay, so weird trick could be that you jump in the middle of another instruction. That's something you can do with machine code. You can do a jump that somehow falls in the middle of an instruction, and this is legit. The processor doesn't understand, hey, I'm jumping in the middle of an instruction. The processor doesn't care. You jump here, bam, you keep executing. In David, that's not the case. Before you execute David bytecode, the verifier actually checks that, for example, you jump at the proper places, or that if you call a method, you're going to call the method with objects that are compatible with the arguments that the method declares as arguments, and so forth. Okay. This also means that I mean, without tricks or without bugs, it's impossible to hide an invocation of a method. Okay, so if you want to invoke a method, you need to do invoke dash something instruction. Okay, so it's going to be there. You're going to see it. Of course, it's possible to somehow make your life a bit more difficult, but you know, there are at least a number of properties that that need to be verified. Now you could say, oh, you know, but can I bypass the verifier, or can I just suppress the verifier, or can I just disable the verifier? And no, you cannot. If you write a malicious app, you write a malicious app to be installed on, for example, my phone. My phone, you don't control if I use the verifier or not. Okay, so once I start the app is about to start, the verifier kicks in, and the verifier then is going to kill your application if you do some weird trick. Okay, but your app cannot really disable my verifier. Okay, and so it's very strict. And again, there are specific properties. Are the bad guys out of luck? Well, not really, in the sense that there are still some obfuscation tricks. Okay, so what you could do is reflection. Where, as we seen last time, the target methods are specified via strings, and strings can be easily obfuscated. But at least reflection is actually called through an invocation of a method. I think it's method.reflect, let's say. But this method invocation needs to be there because it needs to be done in bytecode, and in bytecode you cannot hide this stuff. So again, the verifier enforces certain rules. You can still do obfuscations, but you as the benign guy, as the reverse engineer, you know that at least you can trust a number of things you see in the bytecode. Okay. Other tricks to bypass these things was the dynamic code loading. Again, the verifier verifies the bytecode yes, but then as a method call you can do please load another piece of code, and of course the verifier is not going to try to understand what kind of piece of code you're downloading. Okay. However, if you download another piece of code, the piece of code you're downloading, if it's actually Davi bytecode, again, it needs to be verifiable Davi bytecode. So again, there are some checks, and then the malware needs to be the malware author needs to be some kind of an artist to somehow try to obfuscate things, but still comply with different rules. One different thing is the native code. Native code, again, it was the right part of the first slide, where from C++ you go to directly machine code or to the shared object files. Reliable, once you have the machine code, life is getting complicated. Reliable disassembling of arbitrary native code is still an open problem, okay? Because in native code, you can do many more tricks. You can jump in the middle of the instruction. You can somehow compute some numbers and then jump depending on the result of these operations. And it's sometimes very tricky to understand exactly what's going on. You cannot do this trick with Davi bytecode. So somehow disassembling Davi bytecode is relatively easy, and there are tools that do it, and they do it very well. And reliability assembling native code is very complicated. There are tools that do it well, but there are ways for a malware author to actually really complicate your life and maybe trick these tools, okay? There is no such thing as a native code verifier. If you have a piece of native code and the processor starts executing it, bam, the processor is going to start executing it. There is no check before that says, oh, this code is good or not. There is actually one thing called Google Native Client that somehow has the same spirit of the bytecode verifier, which is a component that somehow takes a piece of machine code and says, okay, it respects the rules of Google Native Client, then okay, I load it, otherwise no. Don't be confused by this. This Google Native Client exists, and it's used a lot in the context of browsers, or I think maybe the Chromebooks. For I think maybe Chrome extensions, but it's not used on Android. Okay, so machine code in libraries that embedded in Android applications are not checked with any kind of verifier, so they just run. But again, this idea that you take a piece of code and then you try to check before executing it if this piece of code satisfies certain properties, then it's going to be explored also in the context of machine code. And again, one popular implementation is this Google Native Client. But again, I mentioned this for completeness, but it's not used in Android as far as I know. All right, back to Davi bytecode. Want to give you more details. Again, I guess you know where I'm going with this, right? You go from the author of the app goes from Java to Davi bytecode, but now us, the reverse engineers, the ones that from an APK need to understand what's going on, well, from the APK you unpack it, you get classes.dex, then you can maybe transform this classes.dex, which is Davi bytecode, in a more human readable version of it, but it's still Davi bytecode. And from this Davi bytecode, we need to understand what's going on. So it's very important for us to understand how this David bytecode looks like and so forth. Okay, so here, this is why now we have more information about this. So one cool part about the David bytecode is that it knows about object-oriented concepts. So machine code is just a bunch of instructions. They just know about registers and memory. But David bytecode has the concept of classes, methods, fields, the fact that given an object, given a class, you can create an instance of an object, and so forth. And for example, in the previous snippet, we have seen there was an invoke virtual or something like this. This already should convey the fact that David bytecode knows about object-oriented, okay? Because invoke is basically, you take as an argument the instance of the class you want to invoke the method on, and then the various arguments. That's an object-oriented programming concept, okay? Same for fields. There are ways to get or set fields and so forth. The syntax in general is the classic Intel syntax, where basically we list the registers, and the first one is the destination, the other ones are the source arguments. So for example, one instruction could be move R3, R2. This means move the content of the register R2 into the register R3, okay? Dalvik knows also about types. Again, that's something the machine code does not have it. So types could be, we have the list, void, byte, short, char, integer, boolean, and so forth. And again, as you can see here, basically in the Dalvik bytecode representation, each type, at least the built-in types, are represented by one letter. Okay, so if you see V in a type, it means void. If you see B, it means byte. If you see Z, it means boolean. Okay. And then as a type, you actually can have an actual class as a type. So the one in the first line are built in, but you can also have classes. And classes are represented in this way: L, and then the fully qualified name, so package name and the class name, and then semicolon. Okay. And two examples. There's the type identification for Dalvik, of the intent class. Intent class is defining the package and the content, and so that's it. L and reduced content oriented. And again, as you can see, each of the item in the package name and in the class name are separated by a dot. Okay. All right. So once you get this David bytecode from this class to DEX, there are tools to somehow read all the content, and somehow these tools split the David bytecode in different files. There is one file per each class. So for example, if you have class A, class B, you're going to have file a.smally and b.smally. We're starting to see this smally. What is smally? Is the name of the human readable representation of this David bytecode. Okay, so again, David bytecode is actually some binary stuff, but then humans somehow came out with this format called smally to somehow have a textual representation of this David bytecode. Is somehow the analogous of the assembly for machine code. Okay, so when you see smally, it is what it is. And so these programs that somehow takes this David bytecode, raw David bytecode, and converts it to smally, usually they output one file per each class with the .smally extension, where A is the actual name of the class, and usually they put this file in a folder structure that reflects the package name. So for example, if you have the class pig in com.peppa package, usually you're going to get folder com with folder peppa, and in this folder peppa you're going to have pig.smally, okay, which contains all the code relevant to the class pig. And in this class pig, usually you have all the methods nicely split. So if this class pig contains method foo and method hem, you're going to have method foo code and then method hem code, very nicely separated. Again, in machine code, it's tricky. Even to get where the each function starts, it's complicated. while in Smiley, it's actually well defined, okay? Now, other properties of Dalvik. Dalvik is register based. So there is the abstraction of registers. So each method has a bunch of registers, and then this register are called, let's say, V0, V1, V2, V3, and then they can store some objects, and then you can move values from a register to another one. A very important thing is that each method has its own register frame. What does it mean? This is very different than machine code. So in machine code, you probably heard that there are registers as well. So in x86, there are, for example, EAX, EBX, ECX, and so forth. And if you have a function here, and then you set registers here, and then you say, we jump to another function, okay? These registers are shared. If I modify the value of EAX here, there is only one EX in the processor, okay? So once I go back here, the register EX is gonna have a different value, okay? In Dalvik bytecode, it's a simulated code, right? It's the DVM somehow executing this bytecode. And it turns out that each method has its own frame of registers. What does it mean? It means that if you have function 1 with a bunch of registers, once you call to function 2, these registers are completely independent. If you modify register 5 here is not modified at all, okay? So again, each method has its own frame, means this, that each registers, maybe it calls the registers in the same name, V0, V1, V2, but they are pointing to different parts of the memory, okay? Now, other information, I know it's a lot, but then we're gonna have some examples. Let's say that function foo calls function hem, and function hems calls, accept 2 arguments. Where are these 2 arguments placed? Well, it works like this. They are placed, a function hem is going to have its own register frame, and let's say of 10 registers, and the 2 arguments are going to be put at the last 2 positions of the register frame. Okay? So again, each method has a register frame. Each method actually has a frame of size that is well defined. So once you disassemble a method, usually there is written, the size of this register frame for method foo is 10. So this method is going to use 10 registers. Okay. Again, the size of the frame could change depending on the function. Let's say register frame is 10. If foo was getting 2 arguments, we know, and let's say that we have 10 registers, and they're called from V0, V1 to V8, V9. If foo takes 2 arguments, the 2 arguments are going to be put in V8, V9. Okay, how do I know? Well, that's how actually the WVM is implemented. So you know that if you call a method with specific arguments, you know in which registers these arguments are going to be ending up to. Okay. The other important thing is that if a method is non-static, there is an implicit first argument, which is the this. Okay. And it is treated as a normal argument. It's just implicit. What does it mean? Again, let's say that you have function foo with 2 arguments, and let's say the function foo is non-static, which means that it's going to operate on an instance. Okay. So what happens is that function foo implementation actually doesn't see only 2 arguments, but it sees 3. The 2 arguments of foo, and then a third implicit argument that comes before the other 2, that is a pointer to this. Which means that if foo had 10 registers in the frame, V8 and V9 are the 2 arguments, and V7 is going to contain a pointer to this. Why am I keep repeating this stuff and I keep stressing this? Well, because if I don't tell you this, you're going to see methods with maybe 10 registers, and you're going to see this method using value V8. You need to know what kind of value V8 contains to understand what's actually going on. And so this slide tells you, well, V8, V9 contains 2 arguments, and V7 is going to contain this. Okay? Cool. I have more slides on this register frame, but I think it was already quite clear. Let's see if there is some more information. Yeah, here is another example. So let's say that you have a register frame of 6 registers, and then that this method actually takes 3 arguments. So this this method is going to use registers. Well, there are 6 register, frame is 6 sized. So we're going to use from V0 to V5, and the arguments are going to be placed in V3, V4, V5. If the method is non-static, then it means there is an implicit extra argument at the beginning containing the this, and is going to be placed in V2. Okay. Again, I'm stressing out other differences with the machine code, with the CPU register. Again, they are not shared across methods. But pay attention. It could be that a register contains a value that somehow references an object. Let me explain this better. Let's say that you have a function foo that takes an integer as an argument. Well, you call function foo, and then this foo can modify the register the way it wants, and once you go back, the register value is not going to be changed, okay, in the caller. Now, let's say the function foo, instead of taking an integer as an argument, it takes an object, okay? Well, objects are passing objects around is implemented always by reference. So when you call a function foo with an object, you're actually passing in the register a pointer to an object X. Now, in the bytecode, you can actually modify the value here and nothing bad is going to happen. But of course, usually if you get an object and you may want to modify it. If you modify this object, this modification is going to be reflected on the caller side. So the caller is going to see that the object was modified. Why? Well, the value in the register did not modify. It's just the pointer. Okay, and if I change the pointer, the caller is not going to see it. But if I modify an object, usually the value in the register is the same. It's just a reference to the object. Okay, so usually the reference to the object is not going to modify it. Is the memory pointed by this reference that is going to be modified. And that's what we mean with modifying the object. And now once we go back to the caller, the value in the register is the same, but the memory pointed by this register is going to be different. Okay, so that's what I'm rephrasing for the 15th time. If you modify the value in a register, the caller is not going to see it. Why? Because the register frame of each method is independent. But if you modify the memory and two guys point to the same piece of memory and you modify the memory, of course the caller is going to see it as well. Okay, and that's how you can have side effects and things like this, even if the register frame is exactly independent. All right. So more or less everything fits in one register, including objects, because you just store a reference there. But there are two types of built-in types that somehow take two contiguous registers to put the value in. So there are two types, long and double, and again, they takes two registers. Okay, let's see if I have. I maybe have, maybe not. But what does it mean? It means that, let's say that you have a long argument that fits in register V3, and let's say that you only see this V3 being passed around. What's actually happening is that the actual long value is stored in V3 and V4. It's always the consecutive one, okay? And then you need to remember this, because sometimes you pass around V3, but also V4 is used. Well, and you don't see it set, but if you see set V3 with the long, then you also know that V4 it was set. Okay. Sometimes you see that V3 is used and V5 is used, but not V4. That's also usually the reason, because V3 was a long one, and V3, if you set V3 with the long one, you're also filling V4. All right. Now, the best way of learning how to reverse engineering on how to read this Mali code, or how to understand how this Mali code works, is to start with a simple Java program and somehow compiling it, and then somehow extract this Mali code. I need to still explain how to extract this Mali code, but at the end of this class, you're going to understand how to do this. And so you're going to be able to be independent on this. So let's focus on this very simple Java program. We have a class called Peppa, and then one method called pig, which takes an integer and returns 2 times x. And then you have another method, static method, called foo. We take an integer a and an object of type peppa p, peppa. And then we have that in b equal p.pig a, return a plus b, okay? So somehow we take the object peppa, we invoke a method, and we do a sum, and that's it. Cool. Now let's try to understand how these methods are implemented in Smiley. So let's focus on the pig method. Okay, pig method in source code was this on the right. So we take an integer and we return 2 times x, and let's see the Smiley. So first of all, look at this. This dot method tells us, okay, I'm starting to list the implementation of a method, and this is gonna end with this dot end method. Okay, so again, the method beginning and end, they are very well marked. This tells you the method name, pig, and then in parentheses, you have the list of arguments. And these arguments, again, are represented with one letter for built-in type or with this L, package name and class name, semicolon, for objects, okay? So in this case, we take only one integer, and that's why we only have I, and in fact, it matches. Then we have close parentheses, and then at the end, we have another type, which is the return value. Again, in this case, another integer. Here it is. Now we have dot register string. This means that the frame size of the register is 3. So from this line, we already know that the method is going to use v0, v1, and v2, and that's it. Okay. Then here we see that we have an instruction. This is a multiplication of an integer register with a literal of 8 bits. And the semantics of this is the following. Take v2, multiply it by 2, and put the result in v0. How do I know this? Well, because I spent a lot of time trying to understand what kind of this Smiley means. And, you know, if you take this instruction, you Google for it, you're going to find, you know, a list of Dalvik instructions with the meaning of it, okay? So, you know, Google is your friend once again. And again, the interesting thing here is, you know, v2, we do v2 times 2, we put in v0. But what is the value of v2 once we call this? Well, remember, the size of the register is 3. So we have v0, v1, v2. And we have one argument. Where is the argument? At the end of the frame. So if you have v0, 1, v2, v2 actually contains the value, the first and only argument, which is x. Okay? So v2 somehow contains the x times 2, we put it in v0, and then here we say return the value in v0. So we're getting x, we're getting x times 2, and we are returning it. So everything makes sense. All right? Shocking, shocking. Okay, this is the explanation, you know, in case you don't see the recordings. Oh, actually, I forgot to explain this. One question could be, why do we have 3 registers and not only 2? Because here we have, you know, v2 is the integer, and then we are just multiplying this and putting another register and then returning it. What is it v1 about? Well, v1 is the this. What does it mean? Well, method pig is non-static, which means that it's a method that should be invoked on an instance. For non-static method, there is always an extra implicit argument, which comes before all the other arguments, so before x, which is the pointer to this, which points to the current instance. Where is it put? Well, it's used as a normal argument, okay? So this method actually has 2 arguments. One is v0, v1, v2 are 3 registers. In v2 we put x, in v1 we put this, and in v0 it's a spare variable for the internal logic. And so that's what v1 contains, is the this, okay? If this method would have been static, you would probably have only 2 registers, one for the x and one for the return value. Okay, bit more complicated. Let's investigate this method foo. Okay, again, this is the source code. We have a static method foo, which take integer a and then class peppa. And then we do some kind of, we invoke a method on this peppa object, and then we return a plus b. And let's try to understand how this logic in Java maps to the logic in Dalvik. First of all, Here we see dot method. Okay, we are about to start the code for a method. Static, interesting. So as you see in this Mali, it's nice enough to tell you all the access modifiers. So it will tell you if the method is public, private, protected, and so forth. And it also tells you if it's static or not. Okay, so if the method is static, you're gonna see it as the first keyword when you read the implementation of a method. Then this is the method name, open parenthesis, list of arguments. And here we have I, the first one is an integer, makes sense. And the second one is L, okay, it needs to be a class. L, and then we read package name, semicolon. See here, the syntax instead of being with dot is with a slash. So usually actually Smiley uses the slash syntax, other tools use the dot syntax. So depending on the tool you use, you may see the com dot something or the com slash something. Again, Smiley usually uses the slash one. And again, L, com, Peppa, semicolon, that's the type definition for the Peppa object. Close parentheses, and then we return the integer, okay? Perfect. Now we see dot registers 4. This means we're going to have 4 registers in the register frame: V0, V1, V2, V3, and that's it. Okay, these 4 registers are completely independent from the registers of the caller. So if we modify the value of V0 again, we are not going to modify the value of V0 in the caller. Remember this. Now, the first thing we do in the source code is do p.pig.a. Let's see how this is implemented in Smiley, where we have invoke virtual, okay, and then we have v3, v2, okay, and then something like this. Well, again, if you check documentation, invoke virtual is expressed, or it means the following. First of all, at the end, you see the type of the invocation. This tells you exactly on which class you're invoking the method and the method definition. So in this case, we know we're invoking a method on the class com, example Peppa. Kind of makes sense, right? We're invoking pig on the P, and P was of class Peppa, so everything makes sense. And then on this class, we're invoking the method pig. And again, this invoke virtual specifies the entire method signature, the name, the arguments, and the return value. And again, kind of makes sense. We are calling pig, which accepts an integer I as an input, and which returns another integer as a return value. And again, this is the same signature of the pig method we've seen before, okay? So once again, everything makes sense. And then before, here you see the registers used as an argument to this invocation. Again, pig only uses one argument, but there is an implicit one because pig is a virtual method, so a non-static method. He also gets this as an argument, okay? And that's why here we see 2 arguments being passed and not only one. So v2 somehow should be the integer, and v3 somehow should be the this. Let's try to check if it makes sense in terms of registers. Turns out it does. So registers 4. So it means we have v0, v1, v2, v3. Yes. Here we have 2 arguments. And this L, example Peppa is going to be in v4, sorry, in v3. And this integer is going to be in v2. Okay. The method is static, so we are not going to have a this pointing to v1. Okay. So again, we have v3 is Peppa and v2 is I. And here we have v3 is Peppa and v2 is I. Kind of makes sense, right? Because we do invoke virtual on v3 is Peppa. Well, v3 should be the this for this method invocation, and it kind of makes sense. It's an object of type Peppa, which was coming from P, was coming from here, which is v3. Okay, and then p.pig a is an argument, and a where it comes from the first argument. Where was the first argument? v2, bam, and that's why we have v2 here. Okay, so somehow we as humans, we can read this human readable representation, and we can do some kind of tracing to understand what kind of values are reaching this point. Again, v3 is the last argument, so it must be this guy, and v2 is the first argument, so it must be this guy. And so v2 kicks in here, and v3 kicks in here. And so from this Mali, we can somehow go back to the Java representation. Again, here, basically, after we call this, we're going to move the result into v0. So now v0 contains b. And now what it does is to add these two values, V2 and V0, it kind of makes sense, right? V2 was this guy, which is A, kind of makes sense. And V0 is the return value of this Peppa Pig, which is B, kind of makes sense. We are adding them together, putting them in V1 and returning V1. And again, it makes sense. We are returning A plus B, which is V2 plus V0. Okay? So I hope kind of somehow you get an idea about what's going on. The way to learn this is to code your own mini Java application, compile it, try to disassemble it, try to get the Smiley code, as I'm going to show in a couple of slides, and somehow, you know, you somehow try to understand how Java constructs end up being represented in David bytecode. There are many more David bytecode instructions. At this link, you can find more kind of a list of them. And, you know, for example, there are instructions to move constant from, you know, move a constant in a register, or move the value in a register to the value in other registers. Let me drink something. And there are many instructions to do math-related operations. So you can add things and put them somewhere. You can add a number with the register and put them somewhere, and so forth. Again, it doesn't make much sense to learn them all by heart. With time, many of them are recurring, so they're going to stick in your mind. But again, if you don't remember one, just Google for them, and that's it. Okay. Other instructions. Well, we've seen already invoke virtual. Again, there are a bunch of different methods or instructions to invoke methods, and you choose one depending on what kind of method you're invoking. For example, invoke virtual is used to invoke virtual method or non-static methods. Invoke static, surprise, surprise, is used to invoke static methods. So if you need to invoke the method from before, which was static, you wouldn't use invoke virtual, you would use invoke static. Then there is another number of instructions to invoke methods. If I remember correctly, invoke direct is used when to call a constructor, or invoke super, or whenever you don't want to trigger the kind of dynamic dispatch kind of thing. Invoke super is used to call a constructor of the superclass of the class you're extending. Or if you're invoking a method of an interface, then you use invoke interface. Okay, again, check this in the documentation. Oops. We have been seen already how to get the return value out of a function. So sometimes you want to do invoke virtual, okay, and then this guy returns an integer. If you want to access the return value of this function, you need to move this return value into a register. So if you call just invoke, the return value is not placed anywhere. It's placed only in some temporary register that you do not have access to. If you want to have access to it, then the next instruction needs to be move result and then a register name. And basically now V5 is going to contain the value returned by this Peppa Pig. Okay. Again, if you want to do this move result needs to be the instruction following invoke virtual. If you put another instruction here, this move result, I don't think is going to be valid. Actually, I think the verifier is going to cancel it. Okay, actually, check. See. Other things, as I mentioned before, Dalvik bytecode is aware of object-oriented concepts, so it is aware of fields. So a class can have fields, and there are a number of instructions to set and get from these fields. And there are a number of instructions depending on what kind of field it is. For example, to read from a field, you can use iGet or iGet object. Again, I use iGet for, I think, built-in types. iGet object is for reading the value from a field, which is a pointer to an object. Okay, iPut is the same stuff, but to set a field. And then you have this sget, sput is the same stuff, but for static fields. okay, for fields that are not associated to instances or Java classes, but for fields associated to the actual class, so static fields. Another instruction is to instantiate a new object of a given class. Okay, so this MOBISEC Peppa is just the class type, but it's not an instance. If you want to create a new object, so in Java, once you call something with parentheses, so like you call the constructor, in bytecode, this is translated to new instance. So this is going to create a new instance of the class MOBISEC Peppa, and it's going to put this pointer in v2. There is something I did not mention here. Just after this, you are not ready to use this v2. Basically, this new instance just creates the data structure containing the MOBISEC Peppa object, but before using it, you actually need to call the constructor. So after this, usually you're going to have invoke direct v2 init. Init is the method name that usually links to the constructor. Okay. There are other instructions to implement conditionals. For example, this one means if name v0 v1 label a. But this means if the v0 is not equal to v1, then jump here. Okay. Or for example, another instruction is go to here, bam, you're going to jump to b. And that's how loops are implemented. That's how ifs are implemented. That's how if in Java is going to be appearing in Smiley code. Okay. There are also a number of meta instructions. For example, when you need to initialize the big array, you can use this field new array, where basically you put, you can create a big array, and then just in this instruction, you set the pointer to some stream of bytes, and then the stream of bytes are going to be used to be loaded in this array. Again, it doesn't make sense to memorize them all. Here, I just want to give you somehow a survey of the most important types, so that when you see something, you don't scream in horror. But if you don't remember exactly what's going on, Google for it, and it's going to be fine. All right. All right, so that's more or less was my overview about this Dalvik bytecode internals. Again, we did not see yet the tools to somehow extract this bytecode, but you get the idea on how it looks like once you have the tools. Before we go to the tools, I would like to explore, which component is actually executing Dalvik. Okay, I kept mentioning this Dalvik VM, but then I also kept mentioning, but that's not exactly correct, and so forth. So on the conceptual level, what I said so far is correct. You have the Dalvik bytecode, and this bytecode is somehow executed by something like a Dalvik virtual machine, some kind of machinery, some kind of program that takes as input the Dalvik bytecode and somehow execute each of these instructions that we have just seen, so that the behavior from Java that was implemented in Java can be actually carried on. Now, the technical way on how this Dalvik bytecode is executed has changed in the past years. So in the past, so up to Android 4.4, so it's already something like 6 years or so, 7 years, there was a component was actually called DVM, Dalvik Virtual Machine. And it was some program wrote in C++ from the Google people that was compiled to libdvm.so. So if you have the phone, Android phone, this phone will contain libdvm.so, and this library was able to get an input Dalvik bytecode and somehow execute it. And that's how apps were working. Okay. And the way it was working is that you have the APK, and the APK contains the Dalvik bytecode, and once you run it, before running it, you cannot just execute Dalvik bytecode. You somehow need to, this DVM would take this, somehow compile it on the fly, and run it. Okay. Somehow we can call this some kind of compilation on demand, in the sense that it's not that everything is compiled, let's say, but it's on demand. And we call this just-in-time compilation. Okay. and the code that is compiled is actually stored in the cache. Okay, cool. Then at some point, the Android people came up with Android Art. Art stands for Android Runtime, and it replaced the old Davi virtual machine. It was introduced on Android 4.4 as optional, but then in Android 5 it became mandatory. This Android Art implemented what's so-called ahead of time compilation, and this meant that the compilation happens at installation time, app installation time. What does it mean? Well, it means that with the VM, you basically install the app and that's it. Once you run it, the VM will start taking your Davi bytecode, compiling and executing it. With ahead of time compilation, this compilation would happen at installation time. So once you install the application, the framework would somehow take your app and compiling it. And then once you want to run it, bam, it's already compiled, super fast, okay? Now, one thing to understand is the various pros and cons of this art and the VM. So I have some slides to discuss this. So in terms of pros, this art, you know, the app's boot and execution are much faster, okay? Because, you know, once you start the app in art, it's already compiled. You just need to jump to the compile code and run it. And also the execution is not that there are some methods already compiled or not, you know, it's everything already compiled. The big cons is that, one of the cons, let's say, is that art takes more space on RAM and disk, okay? It's really, depending, I mean, given the way it was done, basically every installed app would be already compiled, and so it would occupy a lot of space, okay? But the major cons is that the installation time takes much longer, because now once you install it, you need to wait that the framework would compile the entire application, and only at that point you could use the app, okay? Now you could say, okay, whatever, why should I care that that, you know, the installation takes longer? Well, this had a very bad repercussion in the entire system, because it's not just the installation of your Flappy Bird app or Angry Birds app. Is that if there is an app update, well, app update means that you're getting a new app from the store, and now to do this update is going to take longer. But this is the same also when you have system upgrades. Okay, so when you have a system upgrade, for example, some inner details of this idle time compilation of this Android runtime, this art will change. And so once you upgrade the system, all these Android apps will need to be recompiled to target the new system. And this will take a long time. So sometimes you have an update of the system, and then you need to reboot, and now you need to wait 15 minutes, even more, 20 minutes, or whatever. Okay, this pissed off a lot of people. Okay, and you know, I think we are too young for this, but you know, up to 3 years ago, getting this kind of pop-up was quite frequent. You update your phone, you reboot it, and then you're stuck with this optimizing app, whatever. Okay, and it would take a long time. This brought the Android people to move to a new version of art. It's a mix. Is, you know, with technical terms, we can call it profile-guided just-in-time compilation or ahead of time compilation. It was introduced in Android 7, and the idea is that art profiles an app and precompiles only the hot methods, the ones that are most likely used. Okay, and other parts of the app are left uncompiled. So it's a kind of a mix of the two words, where basically we precompile only the methods that maybe happen to be executed at the beginning, and we leave everything else uncompiled. If we need to compile it, we're going to compile it later. Okay. It is actually pretty smart. It somehow figure out automatically what kind of methods are more likely to be in need of being used very recently, and they actually do this precompilation when the device is idle or charging. Okay, so they don't, they try to not be disturbing. And the biggest pro here is that to install or upgrade an application or to install and upgrade the system is actually much faster. Okay. And here in this table, I try to systematize the various aspects. So of different, DVM is the initial one, ART is the second one, ART JIT out is the last one I just described. And on the rows, you have the different aspects. So the boot time, the speed, the installation time, how much it takes to upgrade the system or how much this is uses. And as you can see, the last method is somehow a trade-off in all these different aspects. And somehow it seems, that the Android folks managed to hit the sweet spot for all these aspects. And, for ART, there were many complaints. And to be honest, I did not hear much complaints or many complaints for this last kind of ART implementation. Okay, so I believe it's a kind of a success of the team. All right, so I also want to go a bit deeper on different file formats that you may observe if you dig around the emulator. So if you install a rooted emulator, you see around a bunch of files, you're gonna see some kind of different extensions and different file formats. And I would like to give you an overview of these guys. So ODEX is the first one. It stands for Optimized DEX. So usually you have a DEX that is the Dalvik bytecode, and then there is a tool called DEXOpt, with which you can obtain an ODEX. Okay. Again, ODEX is an optimized DEX. It is faster to boot and run, and the idea is that normal apps usually they are not ODEXed, as it said, but what's going on is that usually the system apps that are started and booted every time are actually ODEXed. Okay, so the system apps that are starting at boot are ODEXed, so that once you boot the phone, everything is much faster. Okay, the ODEX is not part of the APK, so the APK is shipped with the DEX. The class is ODEX, which contains the normal Dalvik bytecode, and then this ODEX is specific to the current Android version you have on your phone. And so basically they take, either it comes precompiled for your specific phone, or this can happen on the phone, but somehow in addition to your APK file, you're going to have an ODEX file. And so the system, if it sees the ODEX file, is going to execute the ODEX file. The concept is that it takes space, and again, it's device dependent. It is still bytecode, but it's device dependent. So there can be ODEX instructions that are only available on this specific version of your frameworks, and so forth. Okay, but so what I'm trying to say is that while you can take the DEX and run it wherever you want, because the Dalvik virtual machine is going to take care of differences of the different versions of the Android framework, with ODEX you are not guaranteed that it's going to work. Okay. So ODEX was something that was part of the DVM world. In the new ART, the analogous is a bit tricky, and there are two different formats. The first one is called ART format. I mean, these names are a bit screwed up. There is a lot of overlapping, so I apologize, but not my fault. So I'm not going to take the blame for this. The first format is usually with this .art extension. It contains pre-initialized classes and objects. That's really different than what we have seen so far. So pre-initialized classes and objects means that, let's say you start the system, and there are objects that are, you call the constructor on them, and then you set the fields. And then let's say you take a memory snapshot, okay? This memory contains this class pre-initialized or initialized. So the ART format is a format that somehow is able to capture a snapshot of a specific set of objects already initialized, all right? And then we have the OAuth file. OAuth file are compiled bytecode to machine code. And they are OAuth files, so the extension is OAuth, but in practice is an L file. It's like a Linux binary, okay? So inside it can contain one or more DEX files. And again, it's like an L file that contains compiled bytecode to machine code. And this OAuth file, usually they contain both the original DEX code that generate this machine code and of course the machine code, okay? And the tool that is actually used for this is called DEX2Auth, and it's usually run at installation time, okay? On the device. Again, this is device specific. The confusing part is that even on this art, you still have ODEX files. But these ODEX files now are not ODEX formatted, but are OAuth formatted files. Okay, so this ODEX meant optimized DEX for this DVM stuff, and they were actually, this format was ODEX. Now they kept the same extension, but these are now OAuth formatted files, which turn out to be just ELF files. It's a mess. It's not my fault. I'm not going to take the blame. Okay. Now these two formats, this art and OAuth, are are what they are. The art one is quite interesting. Is that the pre-initialized snapshot. So how are they actually used in practice? Turns out that the art format, there is only one file on the system that uses this format, and it's called boot.art. This boot.art contains the pre-initialized memory for most of the Android framework classes. And it's a fantastic and huge optimization trick. So these guys basically, they create this crazy format just for this Android framework, and I think actually makes sense. So once you boot the phone takes a while to somehow create these Android objects and then somehow initialize them. This boot.art contains a snapshot of the memory, and it takes a lot of space on your phone, but turns out that once you want to reboot your phone, they just take this file, they load it in memory, and that's it. They don't need to reproduce all the steps to arrive to that point. It's very powerful. And for what concerns the OAuth file, there is one important file called boot.auth, and it contains the precompiled version of most important Android frameworks libraries. Okay, so all the traditional ODEX files are now OAuth files, and there is a tool to spec them. It's called OAuth, and again, is platform specific or Android version specific. So if you have an OAuth file for Android 8, you need to have OAuth compiled for Android 8. Otherwise, it's very likely that it's not going to fly. Now, when a new app is starting, what's going on is that it's not that everything is going to start from scratch, but all apps processes are created by forking Zygote. Zygote can be seen like the init of Android. So on Linux, you have this init, and then from init, init starts all the different processes. Zygote is more or less the same for Android, where basically is the first process that starts at the beginning. But in Android, it also has a different role than init. It's also used as a template process for each app. So Zygote somehow contains this pre-initialized stuff in memory, and if you want to start a new app, they fork from Zygote, and now the app is customized with the application code when it starts. And that's again a huge optimization trick, so that many of the things are actually reused. For example, for Zygote, boot.auth is already mapped in memory, and once you create a new app, you don't need to spend time remapping this boot.auth. It's already there. Okay, so there is no need to reload the framework. I took this picture from Stack Overflow. You can see the link here. It somehow tries to systematize how the various things fit together. So again, let's try to figure it out. So here we have an APK, and we obtain the APK from the source. This could be usually, Java. In this case, it's Java. And we obtain a DEX file. And here we also have resources like images and so forth, and native code. And somehow we take native code produces shared objects, .so files, and somehow these resources, native code, and DEX files are zipped together, compressed, and put in APK. Okay. Of course, this picture is not complete. There is also the Android manifest and so forth. I guess they're all depicted here, but you get the point. Now, from this APK, you can install it on the device, and it's going to obtain two things: DEX file and the resource native code. And DEX file in Dalvik, when there was DVM, this dex file was used to create odex file, and then it was executed somehow. Well, in this case for art, this dex file is going to create a OAuth file, which is actually an L file created with dex2auth, and this is executed by the art framework. Okay, while this native code is executed directly by your processor. And that's another reference where basically all these are Dalvik, native, and so forth. They can access the Android framework libraries. But you know, I really like this picture. It's a mix of an overview between, you know, with what's going on inside an APK, and also what's the difference between this Dalvik and this art. Okay. Cool. There are some links with more information. And I also saw a while ago a CTF challenge where basically it involved art and OAuth. Maybe it can have interesting information for you. It was an interesting CTF challenge. Again, I think I was given an OAuth file, and I need to reverse engineer what the app was doing. Usually it's not difficult because the OAuth file is an F file, and it contains both the machine code but also the Dalvik bytecode. And if you have the Dalvik bytecode, understanding what it does is usually quite simple. But for this challenge, what the authors gave us was the OAuth file with the Dalvik bytecode stripped out. So somehow we need to reconstruct the behavior from the machine code only, and it was quite tricky. And again, the link on the slide is going to be a description of how we solved the challenge. All right, last few slides about the tools that we can use to start from APK and go back. All right, first of all, as I mentioned before, the APK is a zip file, and we can do unzip. And inside you're going to find a bunch of compressed stuff that you cannot read and a classes.dex. Okay. If you take this classes.dex, there are two tools that you can use to disassemble them and somehow obtain this textual representation that we've seen so far, that I also call Smally. The tool is called Bugsmally, and you can use it in a way like this. Bugsmally, classes.dex, they show output, and basically this is gonna disassemble the classes.dex and somehow put it in the output folder, okay? And again, each class is going to have its own .smally file, and in each Smally file, you're going to see the Dalvik bytecode in Smally format. To assemble the Smally file, you can use the Smally program. Again, you take a folder with all these Smally files, and you can get back the classes.dex. Okay, here I think is a typo. Here it should be the classes.dex, not the patch.apk file. The main tool you're going to use is APK tool. APK tool is somehow is great, and it somehow is using packing several tools inside. So for example, is able to disassemble and assemble classes.dex because it embeds back Smally and Smally, but is also able to unpack and decompress resources such as Android manifest and various resources. If you don't use APK tool, if you use only unzip, you only see this compressed Android manifest, which you cannot read. But with APK tool, you're able to actually get the actual decompressed Android resources, Android manifest and resources. The way you use it is very simple. After you install it, again, check documentation, you do APK tool D, this stands for decode, APK, they show output. And this is going to take the APK and somehow unpack it in a folder called output. And in this folder, you're going to see the Android manifest, which is now uncompressed. So you can really open it and you're going to see the Android manifest. Same for resources. And then you're going to have a folder with the Smally code, basically. If you want to take this unpacked representation and build an APK, then again, you can use APK tool with the B, which stands for build. You take the folder and then you can basically obtain an APK as output, okay? Now, at the beginning of the class, I mentioned that each APK needs to be signed. So when you repack it, if you modify it a bit, or even if you don't modify it, the APK you obtain is not signed. It's fine, but you cannot install it. If you try to install an APK like this, it's gonna say signature not found or an error like this, okay? So you need to sign it. How do you sign it? Well, again, there are some tools. This, you know, nowadays is very well documented. If you look for how to sign an Android app, you're going to find many resources. But I remember when I started working on this in end of 2011, I really struggled to find how to actually sign APKs by hand. And so here it is in one slide what I did. I wrote a script 10 years ago and I still use it to date. The first thing you need to do is to generate a key. You can do something like this. And then once you have the key, you can use jar signer to sign this app.apk with the key that we just generated. Okay. Again, the key can be self-signed, it can be a debug key, whatever. As long as it's signed, the Android phone is going to let you install it. Okay. There is no check that the signature, you know, is signed by a well-known certificate authority. Nobody cares. It just needs to be a signature that needs to be valid. So yeah, if you try to verify the signature, it should verify, but it doesn't matter which kind of key is signed. Okay, let me do more. So one slide on disassembly and decompilation. These are terms that people confuse often. In most resources you're going to find from reasonable people, disassembly means we go from classic text binary file and we go back to some kind of assembly or, you know, bytecode in some kind of human readable representation. For David bytecode, we have the Smiley human readable representation, but for machine code, we have the same thing, where basically machine code is a bunch of bytes, but then you can go back to the assembly representation, which is something like move from EDX to AX. Okay, so this is what we mean with disassembly. The other term is decompilation. The compilation is more complex and it's about going from the disassembly version to the source code. So for machine code, we will go from assembly or bytecode, or from assembly to source code level representation. So for machine code, we will go, you know, to C level or C-like representation. For David bytecode, we will go back to Java source code. Okay, or for Java bytecode, we will get back to Java source code. Okay, you can have the same, of course. You can have a decompiler that goes from Java bytecode to Kotlin, for example. But you get the idea. We go from some kind of low-level representation to something like a source code level representation. That's the compilation. Okay. Again, with disassembly, just we go back to some assembly level, human readable assembly level representation. Don't get confused. Now, somehow disassembling is easy and trivial for David bytecode. We can use APK tool, it's well implemented, it works. For machine code, there are several tools, but is not a perfect, you know, it's not a perfect routine or a perfect algorithm. There are some tricks that the malware author can use to make sure that the disassembly is triggered. About the compilation, decompiling bytecode is not always possible, but it's very often possible. So you know, you can actually do this. And again, there are some tools in the next slide. While decompiling assembly, it's much more complicated. Again, there are tools that can do this, but it's much easier for an attacker to somehow you know, make your machine code so complex that it cannot be really easily decompilable. In terms of how to decompile, so for what concerns the David bytecode, there are several tools. Jab is probably the best out there. It's very, very expensive. I haven't used Jab in a very long time. Then we have bytecode viewer, it's pretty good one. And then we have JadeX. And then we also have Gidram. It's a kind of recent open source tool developed by NSA, which can also decompile the David bytecode and Android apps. The other trick is to use a Java decompiler. The trick is that we can go from David bytecode to Java bytecode with some other tools. One of them is dex2jar. And then once we have the Java bytecode, we can use the compilers for Java. And so one that I was using often is this JD GUI, okay? Turns out, I think that this bytecode viewer somehow is a wrapper around this dex2jar and JD GUI. So somehow it converts this from David to Java bytecode and then from Java bytecode to Java source code. This assembling is very easy in David bytecode, so APK Tools usually does a great job. The compilation could be tricky, so these tools are not all the same. If one doesn't work, maybe the other one works. Okay, so if you get stuck with one, try with another one. You may be luckier. Again, I have some slides and kind of summarizing what I already said about what is simple, what is not. Again, to recap, the compiled bytecode is usually simple. Even these open source and free tools, usually they do a good job. Of course, there are some techniques to make this kind of decompilation as difficult as possible. And again, there are techniques called packing, where basically take your sample, your app, and try to scramble it together so that it's not easy anymore. And sometimes they use this by mixing it with native code, making your life difficult. So even if you only focus on David bytecode, there are some tricks to make this decompiler crash, or to make this decompiler returning not really accurate result. And one trick that I often use, some more tricks I use also for the challenges, are to use a lot of try catch, and the compilers are not very good in handling try catch. Okay, and so if you really cannot use the compiler, or maybe if you can use the compiler and then you notice that something is weird, then in that case you gotta read the bytecode. Okay, thanks God this bytecode is not extremely complex, so somehow manually you can somehow try to understand what's going on. But yeah, so the compiler, if it works, great. Otherwise, try to understand what the bytecode does. The good news is that you can trust the bytecode, because disassembling the bytecode is actually simple and it's reliable, because somehow it needs to satisfy some properties. Why? Because there is a David bytecode verifier, so it cannot be some random stuff. And this verifier verifies properties that make it easy to disassemble it. So this part should be fine, even if of course for the human is a bit more difficult to analyze with respect to the David bytecode, to the Java source code. Okay, some last tools. One interesting tool is called AAPT. It comes with the Android SDK. Again, if you try to look for this AAPT file, you're going to find it there. It takes an APK as input, and it can dump interesting information such as package name, components, activity, permissions, strings, and so forth. Okay, that's actually the tool. You can use it. You can use something with something like this: APT, dump, badging, and then the APK path, and then I think you specify what kind of stuff to dump. That's the tool I'm using for my system to somehow extract which kind of permission your app needs. So it's actually quite nice. ADB is a tool we already seen last time. It's a tool to interact with apps and devices or emulators. You can list the devices by doing ADB devices. So if you attack an emulator, you're going to see only one, but you can attach a device and an emulator, you're going to see two, and then you can select which one to use. You can install an application by doing ADB install the APK. You can uninstall it by using uninstall and then the package name of the app. Yeah, last time we've seen you can do loadcut. Again, I really hope you already started playing with this for the Hello World Challenge. If you did not, start as soon as possible. Well, you have a month to complete the first homework, so it's up to you. And then if you need to, there are commands in ADB to push and pull files to and from the emulator. So if you do this push file.txt in this SD card file.txt, you're gonna find the file.txt on the SD card. Pull is the opposite. You want when it's useful when you want to pull a file from the emulator. Other commands, so you can do adb shell. You get a shell in the emulator. You can also do adb shell ls. This is gonna basically get a shell and execute ls. And so you're gonna basically see the ls inside the device. And there are a number of other commands that somehow, for example, adb shell am start the shen. The command is am start the shen, and you can do adb shell and then run inside the emulator am start, or you can do this from outside. You can do adb shell am start. Both ways are fine. And again, the program am is to communicate with the activity manager, and in this case, it's basically you're starting an activity. So do am start, and then you pass which activity you want to start. Okay, or pm is the command that plays with the package manager, and that's how basically you can grant a permission. So you can do package manager grant to this application, identify the package name, permission X. And again, that's the command I'm using for my system once I need to give you permissions. And then you have the command dump sys. It dumps a number of interesting information. Again, there is no need to remember this by heart, but if you're curious about how things work, feel free to play with them. And that's about it, guys. Again, these are more information useful to understand how from an APK we can go back to the source code, or to understand what's going on. And if you need to be a bit more motivated, and if you are wondering, is this stuff actually useful in the real world, I welcome to check this link. The first time I had this slide was 2 years ago, when I first gave this class, and the day or 3 days before I gave this class, there was an article of an Italian guy that basically somehow downloaded an app used for vending machines in Italy, and somehow tried to understand how the app was saving how much money you had for the vending machine. And he found out how this stuff actually worked. He found out exactly where the app was storing the amount of money, and by understanding how things work, well, he could modify them. So he somehow modified them to give them himself, I don't remember, 1,000 euros. And so he had free access to these vending machines. I think this guy was threatened to be sued. I don't know how it went, but the article is still up. I just checked. So it's an interesting story. But you're students, you love free food. So if you need to have some kind of push and motivation, that's a thing, a good article. All right, I think, yep, that's what I have for today. Next time, we're gonna have a demo where I'm gonna showcase some of these some of these tools. And in the meantime, guys, check the homework out. You should have all the information needed for this homework already. If you have any questions, please shoot me an email. And if you get stuck with something, shoot me an email. And if you ask simple questions, I'm just telling you, check on Google. I'm not gonna spoil you anything, and you're not gonna be penalized. Okay? Try to have fun. Do not cheat or do not get caught. And I'll see you next week. Bye bye.